Welcome to the 37th lecture. So, today we are going to talk about complexity theory, or more specifically we will give a brief introduction into what complexity theory is. Okay. So, for the rest of this course we will keep our focus only to the set of decidable languages. Okay. So far we have seen several class of languages, and for the past few lectures we have been our focus was mostly on the set of undecidable languages. We saw various undecidable problems, and last lecture we saw a mechanism which we can use to show that languages are undecidable. But from now on we will only focus on the set of decidable problems, and we will give a finer gradation, we will give a finer classification of this set of decidable languages. Okay. So, as I said that we will focus on the class of decidable languages. So, therefore, from now on we will assume that all our Turing machines are halting Turing machines. Okay. Of course, unless otherwise specified. If I specify something else, then of course we will assume otherwise, but by default we will assume all the Turing machines are halting Turing machines. So, what do we study in complexity theory? What are the kind of questions that we want to address? So, first what we will do is that within the class of decidable problems, we will classify them based on the amount of resources that a particular language uses, or a particular Turing machine of a language uses to reach its answer. Okay. So, resources can be many things. Resources can be time, they can be space. So, if you are looking at, let us say, time as a resource, then we will try to see how much time does it take for a Turing machine to come up with its answer, and depending on the amount of time we will classify language into different classes. Okay. So, class of languages which take more time should be in one class of languages which take lesser time should be in another class, and so on. Similarly, for resource like space also we will give a space based on the amount of cells that the Turing machine uses to come up with its answer. Okay. So, first so this gives us classes, and then we will try to, and then we will study relation between these classes. Okay. So, that is the goal of complexity theory, that how are these classes connected to each other, okay. Whether we can show the classes are the same, whether we can separate the classes, what kind of separations are known, and so on. So, these are the kind of questions that we try to address in complexity theory. So, first we need to define what we mean by running time and space used by a Turing machine. So, let us look at a few definitions. So, let M be a deterministic Turing machine. The running time of M is said to be T, which is a function from natural numbers to natural numbers, if for all x in sigma star. So, if for all x in sigma star, m halts in at most order t of mod x number of steps. Okay. So, we say that the running time of a Turing machine is some function t if for every x the machine halts in at most order t of mod x steps. Okay. So, there are several important points in this definition. First is that we always compute the running time as a function of the length of the input, okay. And not only for running time, even when we look at the other resources such as space, the amount of resource that is used by a Turing machine is always a function of the length of the input. So, if x is my input, it is a function of the length. Okay. Next is that, so here we talk about the running time. So, we say that the running time is t if on input x the machine m halts in at most this many number of steps. Okay. So, it can halt in much fewer number of steps also, but it should not take more than this many number of steps. And the third point is the use of the order notation. Okay. So, remember that by the use of order notations, we are actually ignoring multiplication by constants and lower order terms. Okay. For example, if t is, let us say, the function n square, okay, it maps n to n square, then we say that the machine has running time n square if for every x the machine halts in at most order n square number of steps. Okay. So, it can take, for example, n square plus n or 100 n square minus 2n plus 3 or any such thing which is which belongs to the class order n square. Okay. So, similarly, we define the space required, the space required by m is said to be the function s going from n to n if for all x in sigma star m uses at most order s of mod x cells in its work tape. Okay. So, one additional point that is important here is that when we are looking at space complexity, it is important that we keep in mind the model that we defined or we discussed last time. Okay. So, we have a Turing machine, not last time when we talked about reduction. So, we have a Turing machine which has 3 tapes: input tape, work tape and output tape. So, when we talk about space complexity of a machine, we do not consider the space used in the input tape and the output tape. Okay. So, they can be anything that is any arbitrary amount. We only look at the space used in the work tape of the Turing machine, the amount of cells used in the work tape. Okay. So, remarks. So, let me quickly mention what I said. So, we assume the 3 tape model of a Turing machine and count the space used in the work tape only. Okay. Second is we always count the amount of resource used as a function of the input length. Okay. So, this is very important. And since we use the big O notation, we ignore multiplicative constants and lower order terms. Okay. So, now that we have defined time and space complex, or we have defined what we mean by running time of a machine and the space used by a machine, we can define the time and space complexity classes. Okay. So, okay. So, let T be a function from natural numbers to natural numbers. Okay. So, this is the time function that we will have. We define the class d time t, or we will just call it as time t, time t of n, as the class of languages L such that there exists a deterministic Turing machine M having running time T of n such that L equals L of m. Okay. So, time T of n consists of all languages for which there is some Turing machine that has running time T of n and it accepts the language L. Okay. So, basically all languages for which we have some algorithm or some program which runs in that many number of steps. Okay. So, that is the idea. Similarly, for space also we define space T of n as the class of languages L such that there exists a deterministic Turing machine M requiring So, for space, let me use just for more clarity, let me use the function small s of n. Okay. Once again, s is a function from natural numbers to natural numbers. Okay. So, requiring s of n space such that L equals L of n. Okay. So, all those languages for which there is a Turing machine that takes order, I mean that uses at most order s of n number of cells, okay, or that runs in space s of n. So, this is how we define the class time Tn and the class space s of n. Okay. So, in some texts you will also find them defined as d time and the class d space, but essentially they are the same. Okay. So, now we can also define, so all these was for deterministic Turing machine. Okay. So, we can also look at time and space of non-deterministic Turing machines. Okay. So, in the case of non-deterministic Turing machines, we just have to make a call. So, how does a non-deterministic Turing machine behave? So, recall that in a non-deterministic Turing machine, the Turing machine can non-deterministically branch off at every step. Okay. So, at every step during its computation, it can non-deterministically decide to do maybe one of two different things. Okay. So, therefore, it will have more than one computation paths that will lead to a accept or a reject state, and therefore, when we talk about the running time and the space required, we have to be little careful. Okay. So, the way we define the running time of a non-deterministic Turing machine is we look at the maximum time that is required over all the computation paths. Okay. So, whatever is the maximum running time over all computation paths. So, let me just define here. So, let n be a non-deterministic Turing machine. The running time of n is said to be a function t of t from n to n if for all x belonging to sigma star every computation path in n halts in at most order t of x steps. Okay. Similarly, when we talk about the space, we look at the maximum space that is used over all the computation paths. Okay. So, the space required by n is said to be a function s from natural numbers to natural numbers such that n uses or such that every computation path of n uses at most order s of mod x cells on its work tape. Okay. analogously, we will have the time and space classes also for non-deterministic machines. So, we define the class n time T of n as the class of languages L such that there exists a NDTM, non-deterministic Turing machine n having running time T of n such that L equals L of n. Okay. So, similarly, n space S of n is defined as the class of all languages L such that there exists a non-deterministic Turing machine n using S of n space such that L is equal to L of n. Okay. So, this is how we define deterministic time and space classes as well as non-deterministic time and space classes. Okay. So, now let us look at some specific deterministic and non-deterministic classes. In fact, we will define the popularly known classes P and NP. Okay. So, the classes P and NP. So, P is defined as the union over all k greater than or equal to, let us say, 0 of time n raised to the power k. Okay. So, look at all problems that have a running time either n to the power 0, which is constant, or n square or n cube or n to the power 4 and so on. And the class of all these problems is basically P. Okay. So, basically all problems which have a running time that is polynomial. Okay. So, if I say that a language belongs to P, that means it belongs to n to the power k for some k. Okay. So, it has for some constant k. So, similarly, the class NP of n time n raised to the power k. Okay. So, P is widely recognized as the class of problems having an efficient solution or algorithm. Okay. So, as I mean, it is widely recognized that if we have a problem that is in P, it means that we can actually compute a solution to this problem in an efficient manner. Okay. For example, if we have a computer, we can actually write down an algorithm or a code for this problem that will produce an answer in a reasonable amount of time. Okay. So, in quite quickly. On the other hand, NP is said to be the class of problems whose solutions can be verified efficiently. Okay. So, actually in our next lecture we will give an alternate definition of NP, which will make this idea more clear, but I just want to give a perspective of what we mean here. So, there are certain problems for which we can actually solve the problem in an efficient manner in some polynomial number of steps, okay, such as matrix multiplication, or given a graph I want to find out whether I can go from one vertex to another, or given an array, let us say I want to find out the minimum element in the array, and so on. Okay. So, these are the problems that for which we say that there is an efficient solution. Okay. So, these are the problems which are in P. There are some other problems for which it might be difficult to come up with a solution. Okay. So, we do not know how complex, I mean whatever knowledge that we have, it does not seem likely that a solution can be computed efficiently, but if somebody gives us a solution, we can verify it efficiently. Okay. For example, think of the game Sudoku. Okay. So, in a game of Sudoku, if somebody asks you to solve Sudoku, it is more challenging than if somebody gives you a solved board of Sudoku and asks you to check whether it is a correct solution or not. Okay. So, if somebody fills out the boxes and then asks you whether this is a correct solution or an incorrect solution, you can very easily sum up and check whether the solution is correct or not. That is very efficient. But if you have to come up with your own solution, that is more difficult. Okay. So, there are other such problems for which coming up with a solution is I mean conceivably more difficult than verifying whether a solution is correct. Okay. So, that is the in some sense the difference between P and the class NP. Okay. So, next time we will look at more about these classes, we will look at more examples of problems that are in P and NP, and we will also look at an alternate definition of the class NP, which is more in line with this fact which I just mentioned, that NP is the class of problems whose solutions can be verified in an efficient manner. Okay. Okay, so I will stop here today. Thank you.